So this is chapter 11, problem 20. And the basic idea here is that there's a mass on a spring. And so my favorite way to draw this is imagine there's some giant heavy object like cinder block or something like that. And there's a horizontally oriented spring, which has a spring constant K. And this is a massive object on the end that has mass M. And so for every spring, there is always some position at which the spring doesn't store any energy, doesn't provide any force. That's the equilibrium position. And for simplicity, we can treat that as being a position X. Okay, so in this particular problem, we're told that there's a spring constant of 310 newtons per meter, and that this massive object has a mass of 2.7 kilograms. And lastly, it's displaced at a particular instant. It's displaced by an amount of 0.020 meters. I hope that I have that right. And when it's at this position, it's also moving with some speed of 0.55 meters per second. They don't tell us whether it's going that way or this way, so presumably it doesn't matter. Let's go ahead and assume that the speed is going this way at this instant, 0.55 meters per second. Okay, that's all the information they give us. In part A, we're supposed to figure out what is the amplitude. Okay, so the amplitude, remember what that means. Let's think about the characterization of this motion. Generally speaking, the motion of these objects as a function of time, it may depend on a sine, it may depend on a cosine, it really depends on where it is at the beginning, but let's just assume at t equals 0, it starts at 0, and so this would be a sine function, sine omega t. The amplitude is a, it's the number that goes in front of the sine. It tells you how big, or if you like, how far away from the equilibrium it can go. Okay, so that's the amplitude. It's not yet clear, perhaps, how we can get there, but let's remember, if we analyze this in terms of energy, E, the energy, in this case, there's kinetic energy and potential energy, K plus U. It's actually U spring. It's the only kind of energy we care about. At the extremes, when the mass is all the way at the equilibrium position, there's no potential, but it's moving the fastest. So in fact, its total energy is just the kinetic when the kinetic is dominating. Likewise, when it gets to the endpoints, it's not moving at all, so it has no kinetic, but it's stored all the potential. In other words, this is also equal to the maximum potential it can have. This, if we look at what the position is, and we remember this fact that the spring potential energy involves 1/2 kx squared, the biggest that US can be occurs at 1/2 kx max squared, and x max is as big as this function could ever be. Sine can't be any bigger than 1 or minus 1 at the other extreme. So in fact, this is 1/2 k a squared. That's one place where the amplitude comes in, and in fact, this is the only place I can think to introduce it. Now, maybe there's another way, but let's see how we can go through this. We know whatever this is equal to, it will give us an amplitude. So if we can determine the kinetic and potential energy, then we'll be okay. In fact, as long as we can calculate this at any particular instant, we know, because the energy is conserved, this total will be the same throughout the motion. The kinetic is 1/2 mv squared. Let's box this off here. The potential is 1/2 kx squared. And as long as we evaluate this at the same instant, we'll be in good shape. Do we have a mass? Yes. Do we have a speed? Well, we have one speed when it's at this location. Do we have a spring constant? We do. Do we have a position? We do at the same location. So in fact, we have all the information we need to calculate the total energy. That would be set equal to 1/2 times the spring constant, which we have. And so the only unknown quantity will in fact be A, which we can now solve for. All right, so if we compute this, 1/2, 2.7 kilograms, speed of 0.55 meters per second, and square it. Don't forget to square it. Plus 1/2, 310 newtons per meter, and the position at that point is 0.02 meters. Also, don't forget to square it. That's, if you like, the energy. And we're going to set this equal to 1/2 k a squared. That apparently comes out to be 0.47 joules should be the unit if we've done it right. Kilograms, meters, seconds. Yep. Equal to 1/2 times the spring constant times a squared. So now we're ready to find the amplitude. If you work it through, you'll find the amplitude is 0.55 meters, which is the same thing as 5.5 times 10 to the minus 2 meters for the amplitude. Lastly, I feel like this was part A. Okay. Part B, they'd like us to see if we can figure out what the maximum speed is. Well, it's not totally disconnected from this discussion up here. The maximum speed occurs when the kinetic energy is maximum. In other words, this is going to be useful to us. Inside of this should be 1/2 mv max squared. So that may be the most straightforward way to relate it to everything we've done. The total energy we've already calculated, thankfully, 0.47 joules is equal to 1/2 times the mass, 2.7 kilograms, times its maximum speed squared. A little bit more algebra and taking a square root, you should find that 0.59 meters per second is equal to the maximum speed.